basically melt material which is magma that solidifies underground or subsurface. And explosive igneous rocks, this is lava that solidifies above surface. So also remember the difference between magma and lava. Both are molten rocks, molten material, but magma is what we call melt below the surface, and lava is what we call melt above the surface. Okay. So like he said, for intrusive igneous rocks, they are coarsely crystalline, so you can actually see the crystals, and these are coarse, so these are large crystals, because they have much more time to form, because they cool very slowly. And why do they cool very slowly? Because of the blending effect of the above layer of country rocks. Yeah? And extrusive igneous rocks, these are very fine grained, because once it is exposed to the atmosphere, it cools down very quickly, and crystals do not have that much time to form, okay, and are usually aphanetic. Okay. What kind of minerals would you find in a mafic igneous rock? Okay, I'm talking about minerals, okay, not elements, minerals. Mafic ones. Silicates, yes. 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 So you have pyroxenes, an example of pyroxene. You know that? Okay, you can have a lot of olivine. Olivines are magnesium or iron silicates, or a mixture of both. And members are phosphorite and phyllite. So phyllite is an iron rich end member, and phosphorite is a magnesium rich end member. So these are olivines. You can have calcium rich plagioclases, also amphiboles. An example of an amphibole, hornblende. Hornblende. Okay. An example of a pyroxene is orogen. An example of an amphibole is hornblende. So these are all mafic minerals. You usually find mafic, which is iron or magnesium rich minerals in the mafic. Okay. 3. Which of the following types of igneous rocks contain quartz? So is it granite, diorite, gabbro, or peridotite? Okay, looking at the 4 types of extrusive igneous rocks, can you name the 4? So you have mafic, ultramafic, what else? Intermediate, and so you have ultramafic, mafic, intermediate. Just read in the level. Ultramafic, mafic, intermediate, and last one? Felsic. So those are the 4 main groups of extrusive igneous rock. What's an example of an ultramafic igneous rock? Say, a peridotite, which is olivine. Okay. So, for number 3, which of the following types of igneous rock contain quartz? So, of the 4 choices given, granite, diorite, gabbro, and peridotite, which ones do you think will contain quartz? So when you classify rock types, felsic, mafic, intermediate, you are looking also at the SiO2 content of rocks. Okay. So the more silicon oxide a rock has, the more felsic it is. The more it leads towards felsic side. The less SiO2 means it is more mafic. Okay. So if you have a lot of SiO2, that means it is intermediate. Okay. So SiO2, what's the name of the mineral that forms from SiO2? Pure or SiO2? What's the name of the mineral? Silica is Si. That's an oxide. So silicon oxide is which mineral? Quartz. Okay, quartz. Okay. When you have a lot of quartz, the more the silica content, the more felsic, like I just mentioned. So of the four given, granite, diorite, what else? Granite, diorite, gabbro, and peridotite, which are most likely to contain quartz. So this has to be felsic, okay, rocks. So which of the four are felsic rocks? Granite, okay. So you have granite. Anything else? Anything that is intermediate? Diorite. So that's felsic. And diorite. This is intermediate. Okay. So granite and diorite you will expect to find quartz inside. What about gabbro and peridotite? What kind of rock is the gabbro? It is intrusive rock, yes. It is a mafic intrusive. And peridotite? I just told you earlier, like a minute ago. It is ultramafic. Thank you. Peridotite is an ultramafic rock. So ultramafic rock, these have large amounts, more than 70% dark minerals. Okay. Mafic, you see more than 60% dark minerals. When you're talking in relation to dark minerals, then you have in felsic rocks you have less than 20% dark minerals, and then in intermediate rocks you have 30 to 60% dark minerals, and then in mafic it is more than 60%. And then when you go to ultramafic you have more than 7%. Okay. So how does fractional crystallization lead to magmatic differentiation? I know you've already done this during lecture. Number 4. How does fractional crystallization lead to magmatic differentiation? Did I run any question? That was changed. I think the tutorial sheet was changed a bit later. Now it should have 12 questions. You have how many? 9? Should have 12. Fractional crystallization lead to magmatic differentiation. So what is fractional crystallization? Yep. So each mineral has its own temperature of formation. Okay. So once the melt reaches that particular temperature, the minerals start to precipitate out. Take for example, let's say this, for the sake of argument, a magma starts with a temperature of 2000 degrees Celsius. Okay? And let's say olivine, for example, has a temperature of crystallization at 1200 degrees Celsius. So, as this magma is rising up, it starts to cool down. Once the temperature of the magma reaches 1200 degrees Celsius, olivine starts to precipitate out. Okay. Now olivine is a mafic silicate. Okay, so it's an iron of a magnesium silicate. So which one will start? Which end member will precipitate first? For the olivine, you have MgO Fe. So magnesium end member will precipitate first because magnesium is stable at higher temperatures. Okay. So you start with magnesium olivine. Okay, and then it starts to precipitate out first. And because olivine crystals are forming first, and it takes in a lot of magnesium and SiO2 oxides. Okay. So the melt will start depleting in these three elements, isn't it? Yeah? Because all these olivine crystals start to form at that temperature. So, and because this crystal, olivine, contains magnesium, silicon and oxygen, these elements in the melt start depleting. Okay? Mostly your magnesium. So, usually it is the mafic minerals which are stable at higher temperatures. Okay? Mafic minerals are stable at higher temperatures. So as olivine is forming all the mafic minerals, they start to precipitate. Same for after olivine you have hornblende and augite, all these minerals are mafic minerals and they form first. So as they are forming, the melt is depleting in mafic minerals. Therefore it is being changed to the composition of felsic, towards felsic side. So as the minerals precipitate out at higher temperatures, the melt starts to change its composition to a more felsic side. And that is how fractional crystallization causes magmatic differentiation. So after the crystallization of mafic minerals, the residual liquid that is left after the crystallization is more felsic. Five, when the crust, mantle or core, would you expect to find a partial melt of basaltic composition? What are some of the places that melts are of basaltic composition, which means mafic? Which places? Would the Earth's core contain basaltic composition? No, because it's only made up of iron and nickel. Partial melting, remember I talked very briefly about it. Where do you get basaltic formations? Where? Mid-oceanic ridges. That is where you have vessels. Where else? So this is in the crust. Okay. This is the oceanic crust. So at the mid-oceanic ridges, the oceanic crust is very thin because it's very relatively new, which means the pressure exerted on the mantle below is very low. And remember I talked about temperatures of melting relative to pressures. So the higher the pressure, the higher the temperature of melting, and the lower the pressure, the lower the temperature of melting. And because at the mid-oceanic ridges, the crust is very thin, we have partial melting due to low pressures, we are offloading or unloading. Okay. So where else do you get partial melting? Right? Subduction zone in the mantle. Okay. So as the slab is subducting down into the mantle, it is subjected to partial melting. So you get it at mid-oceanic ridges, in the crust and in the mantle. Why do melts migrate upwards? This is a very simple question. You answer. Why do melts migrate upwards? Did you do your tutorial question? I'll see in the next tutorial question. How would you classify a rock that contains, oh sorry, we're still on that question. Why do melts migrate upwards? What is melt? What is the state of the melt? Is it a gas? It's a melt, so it's in what is the form that is there? It is less dense, so it has to do with density difference. And how does it migrate upward? Two ways. One is through melt. You have a pocket of molten material deep below ground and it's starting to move up. What are the two ways it moves up? It's less dense, okay? So it's got a buoyancy factor. And how does it move up then? Huh? I can't understand. Fractures. Okay. It migrates up through fractures. Okay, that is one. What is the second one? Basically by heating the country rock. So whatever its contact comes in contact with, it melts it, and then as it is melting, it is moving up. So it's melting through the country rock. Okay. How would you classify a rock that contained about 50% pyroxene and 50% olivine? Pyroxene is a what kind of mineral? It's a mafic mineral. Okay, and olivine is also a mafic mineral. So if the entire rock is made out of mafic mineral, it is called a ultramafic rock. Or what's the other name? What's an example of an ultramafic rock? Right, this is the fifth time. It's a peridotite. Okay. Okay, who volunteers to answer the next question? Oh, I'm sorry, there are in fact 11 questions. How many questions did I say? Yeah, 11. The 11. Who volunteers the next one? What differences in crystal size might you expect to find between two sills? Okay, so you have two different types of sills. One is intruded at a depth of 12 kilometers, where the country rock was very hot, and the other at a depth of 0.5 kilometers, where the rock was moderately warm. So you have this, let's say that is the country rock. What are sills? What are dikes and what are sills? If you have this country rock, and you have magma rising through the fracture, in such a manner, which one is a sill? Is that a sill? Or is that a sill? This is a sill. Okay? And that's a dike. Or some put it like that. Okay, so we're talking about sills. You have one sill at 12 kilometers. One at 0.5. That's the surface. Now, looking at the question, differences in crystal size. We have that and that. Let's see. The difference in crystal size that you might expect. There is a sill that is at 12 kilometer, where it is much hotter, compared to a sill which is at half a kilometer, where it is much cooler comparatively. What would be the crystal size difference? What do you see? Which one has larger crystals? Which one has larger crystals? Huh? 12 or half? Which one will have larger crystals? 12 or half? You need to attend your lectures, okay? It will be 12. Why is that so? Why will you have larger crystals at 12 kilometer depth? What are the conditions there? It is much hotter at 12 kilometers depth. Therefore, the cooling rate is slower. And if you have slower cooling rate, you have a longer time period for cooling. Therefore, the crystals can grow larger. Yeah. But here, because it is much cooler, once the melt comes in contact with the country rock, it cools rapidly compared to this. Okay. Therefore, the crystal sizes are smaller. Okay. 9. If you were to drill through the crust of a mid-ocean ridge, what extrusive rocks would you expect to find near the surface? And what rocks would you expect to find near the base of the crust? So, if you have this, it's the crust, oceanic, okay, and you are drilling through here, okay. This is surface here. Surface. This is base of crust. Okay. So what are the rock types that you will find here compared to here? We had established already which oceanic crust you have mafic rocks. Okay? Right. So surface would have what kind? What mafic rock would you find? Yes, you have basalts. What kind of basalt? Remember, this is erupting under the ocean, so underwater. So underwater basaltic eruptions will form which signature type of basalt formation? Pillow. You have pillow basalt. Okay. So when you go deeper to the base, what will you find? What kind of mafic rock? You will have gabbros. Yes. Intrusive gabbros. Okay, next one. Why are plutons more likely to show the effects of fractional crystallization than dikes? What are plutons? What are plutons? We've established what a dike is, so that's a dike. What are plutons? Anyone? What are plutons? Any idea what a pluton is? Sometimes as a synonym to an intrusive rock, they also use it as a synonym for intrusive rock is a plutonic rock. So, what are plutons? Plutons are rising bodies of magma or melt material. So, when you have something rising, a body of magma, it is called a pluton. Okay. The question is, why are plutons more likely to show the effects of fractional crystallization than dikes? Now look at the size. Plutons are very large bodies of rising magma, and dikes are narrow. Okay, dikes form through fractures. If there is an existing fracture in the ground, and melt material, attend another session. Melt material is rising through it and solidifies, it forms a dike or a seal. That is through fractures. But plutons, because these are rising bodies of magma, they melt through the country rock and they rise as a density difference. So the main difference is the sheer size of it. Okay. So what the question is, why are plutons more likely to show the effects of fractional crystallization than dikes? Fractional crystallization we have just discussed. It is when minerals start to form at their different temperatures of formation, right? Which means that you need time. If you need time for something, and relative to plutonic bodies or dikes, think why would plutons show effects of fractional crystallization and dikes won't? What's slow? What is slow? Movement? The cooling rates are slower in protonic bodies because it is so large. Yeah? And dikes, because these are very narrow, it will cool very quickly. So there are no times for the process of fractional crystallization to happen. But because protonic bodies are so large and because they will cool very slowly, fractional crystallization can happen in protonic bodies but not in dikes. Yes? Make sense? Next question. What process causes the unequal crystal size in porphyritic rocks? Okay. So who all were in the lab today? Only you were. Do you mind answering? So what is a porphyritic rock? Yeah, so porphyritic rocks or porphyritic texture is when you have large crystals in a fine ground mass. So if you have that, and if you have that, if you look at the rock, this is the fine grain ground mass, and this is crystals that are visible to the naked eye. So you have a very large contrast between the two. Right? You have two different crystal sizes. One is very large, okay, which depicts what? Slow cooling rate, so there is a lot of time for that crystal to form. But then you have a very fine ground mass. How does that equate? What is an explanation for that? Huh? No, not partial melting. Partial melting is what creates melting. Huh? More than one stage of cooling. Yes. And how do you get this more than one stage of cooling? How do you get two different stages of cooling? We have established that the larger crystals were formed through slow cooling process, which means it formed underground. But usually, where do you form fine grains? On top. Right? So what do you think has happened? What? It comes down? No. Take a guess. Just use all that knowledge that you hopefully gain in lectures. Huh? Those actions? No. I'm just yeah, something along that line. So, through volcanoes. So, you have this rising body of magma, which is cooling slowly, and it's forming these crystals through fractional crystallization. Yeah? And then that body of magma suddenly erupts. When it erupts to the surface, it already has these large crystals. But once it reaches the surface, it cools very quickly. Therefore, it forms very fine grain. So the ground mass for the rock is fine grain, but the crystals are larger. And that's how it happens. Porphyritic crystals. During this week in the lab, you will be identifying rocks with porphyritic crystals.